So let's talk about meta-learning, which is a very important topic. And I think about it as a kind of generalization of multitask learning. And multitask learning is a kind of transfer learning. And so it depends on how you categorize these things. But, for example, a child or an infant tends to learn as quick as possible with just one or two examples, want to understand if this is a bicycle or if it is a chocolate. And meta-learning versus transfer learning. As I said, they are different, but they are also similar, because in transfer learning, you have just the task 1 model. But in meta-learning, you have task 1, model 1, task 2, model 2, task n, model n. And for the inference, you don't give some, for example, in traditional machine learning, we give it some data points, but here we give it some task. So you give it task n plus 1 for model n plus 1 that we haven't even seen. And multitask learning is similar to meta-learning as well. You have, for example, you have many different, for example, in image processing, let's say you want to see the background of the image, and simultaneously you have another task. You want to let's say segment it. For example, this area goes together. This area is about kitchen. This area is about dining hall. So simultaneously you want to learn. For example, in speech recognition that I've recently done, you want to simultaneously do NER, name entity recognition, and simultaneously you want to do intent classification. And so of course name entity recognition is very similar. So those networks could be shared as well, but the basis is that you have a shared neural networks, and then you have another neural networks that gives the output of NER. Then you have here another neural networks that gives the output for IC. But you have a shared layer as well. So the weights of these neurons, the weights of this network are shared. In meta-learning, it's similar to that, but as I said, we are learning to learn tasks. So instead of daily life that we give data points to people in the streets, but now we give them tasks. And we evaluate tasks. Instead of evaluating their test data point, we evaluate at their task. So task is the basis of everything in meta-learning. For example, you have 1, 2, 3, 4, 5 classes. So we say 5 classes, and we have, for each class, you have a couple of examples. We want examples to be as small as possible. For example, one-shot example, it means one example. 5 shots. So we have 5 classes and many shots. For example, here we can have 3 shots. And so this is one example, another example, and this is the inference time. But how do you separate tasks? For example, in speaker adaptive training, it depends. For example, in speaker recognition, you give. For example, you have a couple of friends. For each of them, you have a different data set of their speech, and because their voices is different. So task 1 is Farshad. Task 2 is John. Task 3 is Alex, and so on. And so in machine learning translation, these tasks has a good meaning. For example, Chinese, English, German, French, Hebrews, and all of these languages. So it depends on. So the task depends on the language. For example, here we have 5 languages, we have 5 different tasks. And in dialogue generation, we can have different dialogues. For example, one dialogue is about, for example, going to the jungle and spending the holidays and those things. Another dialogue is about doing deep learning and those things. What model do you use? How do you generalize your model and those things? Another one. So in any category, in any of these problems, when you want to separate tasks, it means different things. And there are 3 great methods for meta-learning. One of the best methods, of course, all of them, I like all of them equally for some reasons. Mammal, that lady, I forgot her name, in Berkeley, I guess. Mammal 2017, I will explain it. And I will explain matching networks, which I don't like this. I don't like this because it has a model F and G. I want everything to be united, just one function. I want to estimate just one function. I don't want to have a complex model. So it's against my simplicity rule in artificial intelligence. And the other one is really beautiful. It's proto networks, uses non-parametric ideas because you want to cluster something. For example, this one is like clustering. This one is very similar to this cluster. This is very similar to this cluster. This one belongs to this cluster. It's very similar to that. So this one is non-parametric. So let's review mammal. As I said, that girl was Chelsea Finn in Berkeley, great professor, and here I think she's working in Bayesian approach, Bayesian generalization of her methods. Because I don't know why that recently uncertainty analysis has become very important. It is one of the most important things, but it began just recently that people noticed that it is really important. And so if you can watch his great lectures in Berkeley in YouTube as well, very great lectures. She also reviews basic variational inference and those topics as well. So it's a review for that as well. And so any of these tasks has a different loss. So for example, this task says you should go that way if you want my errors to be as low as possible. The other task says, hello, please go to this way because my task is about Chinese translation. You should go that way. The other one says, no, I'm a German translator. If you go that way, if the weight goes that way, then your German translation becomes better. And then the Chinese said, oh no, Chinese, don't forget Chinese. And the other one says, oh, French, don't forget French mathematicians. If you want to learn French language, you should go this way. So it's a battle between different tasks and different models, but we initialize them very intelligently so that all of them are satisfied. So what? So it's a kind of multi-objective optimization that I created a playlist in my YouTube channel. You can watch that as well. And let's go to MAML. Let's continue to MAML. As I said, we initialize it because the loss of first task, second task, and all of these tasks, for example, we have 5 languages, so L5 is for loss of the 5th language, and you sum all of them and take gradient of them and then back propagation. So everything is very classic. So as I said, you sum all of these losses, and you can do for regression, classification, or any other things that you have, you do traditionally. You can generalize it for meta learning. So here, for individual task, you have a different loss, and finally, in the outer loop, you say that okay, so this one so it's like a multi-objective way direction. It says that you should go in this direction to predict that all of the tasks are satisfied, all of them are happy, and this is the algorithm that I just explained. And matching networks for one-shot learning, as I don't like this algorithm. I don't know. Maybe because it uses 2 different functions, and it is not united. It is not unified, and it's very complex. You know, in machine learning, your model should be as simple as possible. I mean, there is a famous philosophical reason for that. It goes back to Greeks, and so, for example, here is ATLSTM with these rules, and this one is another complex model. It could be anything, of course. It could be LSTM or anything. And then you do, and here is beautiful because you use kernel density estimator, so it's like classic machine learning. I like that. But in this part, you have 2 complex models, makes it very, very complex. And you see if you fine-tune that, sometimes you fine-tune that and sometimes you don't, but the accuracy of the accuracy, if you go down in matching networks, is much better than other networks. For example, the accuracy here is greater in comparison to these things, for example. But next one could improve that, proto networks. By Richard Semmel in Vector Institute in Canada, very nice institute, Vector Institute, and Mila Institute in Canada is also very great. These 2 great institutes in Canada are changing the shape of deep learning. So they are very beautiful places to learn and see the future of deep learning. Proto networks, as I said, for example, this one, first of all, you have a couple of examples in each class, and you take average of that. So C is the average of that. But if you have just the problem of the first, the mammal one, or any other method is that the problem of methods that have one-shot learning. Of course, we can't say it's a problem. Okay, let's just skip that because it's controversial. I don't want to say these things. So let's say, so this is the probability that we want to, you want to maximize the likelihood, and those things you have the cost and then take derivative, everything as usual. But the important thing is that you want to have, to maximize this distance, and at the same time you want the things that, for example, this one is very similar to this, and that's why it should increase. The denominator should increase, and with the other one, which are negative, it should go far apart. And proton networks so you have some. So here you have some episodes. By the way, in meta-learning, people say episodes, so different episodes. And here is the accuracy is much better in proton networks in comparison to matching networks. 49 is a little bit better than 43. And so proto is 98%, while matching networks is just, so they are quite the same. But here, because the task is a lot difficult, it's because it's you are using it for mini ImageNet. This is harder, and it has 600 test episodes. 95% confidence interval. Oh, let's carry on and talk about PAC bayesian for meta-learning. Of course, these things are very new. So I highly suggest this article, Meta-Learning by Adjusting Priors Based on Extended PAC Bayes Theory. I think these two guys are great researchers in Israel. And so here we have McAllister, this beautiful algorithm that I will show you the proof of that in just 4 or 5. I think it was 5 slides. I explained it in lecture 8. So Q is the posterior, P is the prior, and you get this. You want to minimize this, so you add it in your cost function in order to have a better generalization. So we have n different tasks and n different data sets. So you have prior, instead of prior overweights that we classically do in PAC Bayesian learning, because classically you have a neural networks, you have some weights that you want to change it, and you put prior, and then you observe the posterior. And here, the prior, instead of those data points, is over tasks. So your hypothesis is over tasks. And the error becomes like this, because we have an unknown distribution, tau, and then we have some task and data sets, and this is the transfer error. And here is the empirical multitask error. So we can just generalize it, because we have n tasks, so we just add them. So it's very intuitive. Even if you don't like to prove it, it's very intuitive. At least the first one, because you sum them. But here is not intuitive because, you know, this one is different than this one. So you should see the proof of this. But it's the proof is, if you learn the proof of McAllister, you will see how to use that ideas and paradigms and analogies to prove this as well. So we have this optimization. As I said, it's just this cost function over